number 12 here. And in fact, now that we turned on the recording for you guys online, I'm going to say kind of the same thing that I was just saying to the in-person classes. This is not on the exam. This will be on the third exam, so you won't have to worry about it. And maybe that's a good thing because this is pretty advanced stuff. You're going to have some discussions here about viscosity, turbulence, Reynolds numbers. This is some pretty advanced physics, and so there's a lot in here that your author tries to do to get you to appreciate why you need to understand the physics, but it's really going to be impossible for him to go through and for me to go through the equations and to derive things like the Reynolds number and the viscosity. So we'll try to give you some gut feeling, and so there's kind of a balance between, hey, does that feel okay? Does that equation, I'm just going to give that equation and talk about the equation. I won't derive the equation. And you're going to see that, at least in the second half. So you won't see that here today, but in the second half tomorrow, you'll see some more of the advanced stuff. We'll start with the easiest stuff here. And so let's begin our chapter here with what we call fluid dynamics. And so now that we just did a full chapter on trying to understand the behavior of fluids when they are static, let's see how things change or new things that happen when they're in motion. And so let's start off with just taking a tube of some type. I'll call it a pipe. And let's just say that you've got a fluid moving through it. And the first question you just might ask is, what is the flow rate? You know, how much volume flows here? And so let's just put up here volume per time. V over T. And so if this is, say, a blood vessel, you might be saying, okay, or an artery, here's an artery, and say, okay, what is the flow rate? How much blood, what volume, how many milliliters of blood flows every second or every minute through this system? And so the fancy symbol we're going to use is Q. And so Q is our flow rate. How much flows? How many milliliters or how many cubic centimeters? Or if it's a big flow, if this is an engineering problem and this is a city pipe filled with water, or a fire hydrant, we're going, okay, how many gallons every second flow through this pipe? You know, is that enough to serve these people who live down this block? Or is it enough to put out a fire should there be a fire? So we're very curious on what the flow rate is when we're dealing with these fluids. But watch this for a moment. If you kind of look at a chunk of fluid that's flowing, so this will kind of be my chunk here. So I'll kind of make a little cylinder. And the cylinder is moving along. Let's just say that this chunk has a cross-sectional area A. Now, so in this case, it would be the size of the pipe. And I'll just say it has a length of, say, delta X. I could put the volume into that equation by saying volume would be the area times the length. And then if I group the length with time, isn't that the velocity of the fluid that's flowing in there? And so our first equation here for our fluid dynamics is to say that the flow rate is equal to the area of the pipe times the velocity in the pipe. And that, of course, kind of makes sense that it's these two together, the size of the pipe and the speed within the pipe, that determine how much volume flows throughout that pipe. Now, here's why that can be very useful. let's say we have a pipe that looks like this. Maybe the pipe has a very large diameter and then tapers to a smaller diameter. And so if we have a flow rate Q coming into our pipe, it's got to go somewhere. It's got to come out. And so I could argue here, we call this the continuity equation, that, hey, what goes into the pipe has to equal what comes out of the pipe. Now, I am going to put a small subtlety here, and I'll come back to my little model of my liquids. Because if I have a liquid, and we like to use this phrase, incompressible, but even though I'll say that word, I want to point out everything is compressible a little bit. So if I squeeze this hard, it really doesn't change its volume by much. Notice I said by much. I do want to emphasize it does change some. I am squishing them together. You might even think of these little plastic spheres as kind of doing like this, you know, they are squeezing. But they're solid, and so they don't squeeze by much. I mean, you would have to put an enormous amount of pressure to see it squeeze any significant amount. So let's just say that when you put pressure on them, they don't really change their volume. So again, what that would mean is as they are flowing through here, the density here and the density here are the same. So if 1 million molecules come in, guess how many have to go out? 1 million molecules. There's no way you can crowd more in here. It's not like you could put a cap on here and say, hey, put a few more in there. It's not like you're filling up a room with people. I mean, if we would close those doors and let people come in, we would say, oh yeah, there's room, fit right here. Okay, you fit right here. Okay, you fit right here. And we could start having people come in without people going out. But if this room was already shoulder to shoulder filled with people, for that person to come in, that one needs to go out. There is no net gain of the number of people in this room. They got to stay the same. And so I'm going to use that here to say that in the case where I have this narrowing of the tube or widening of the tube, the amount that flows in, and so I'll say 1, equals the amount that flows out. I'll say 2. But then let me use this to my advantage. I would say area number 1 times volume number 1 would then equal to area number 2 times volume number 2. And what you're really saying here is something that has a big area will then have a small velocity. And then as it reaches into something that's kind of narrow, where the area has gotten smaller, to get that same volume through, it's got to go faster. And so this narrowing of a pipe means it goes faster. And that's probably not a surprise to you. Many of you probably have used a garden hose where you can, just have the regular hose, you turn it on and you see the water come flowing out. And it, maybe does this. But as soon as you put on that little nozzle that tapers down into a small area, it comes out at a high rate of speed and it goes shooting up really high. And so what you've done is you have increased the velocity by decreasing the area so that the product of these two remains the same. And so it's the same amount of water that enters the hose is what exits the hose. It's not the same speed. And so we take advantage of this narrowing of the tube. Now, even though I've talked about narrowing it, it would work in reverse. So had we been in the narrow part of the tube going this way, and then it flares out to a big piece, it would slow down. But keep that in mind. I don't think we'll maybe get to quite that far today. Bummer. But you know, I have a pipe here, and there's a big circumference here compared to here. And so when I blow air through here, I'm going to say here it goes slow, but here it goes fast. Then it widens out again, and I'm going to say here it slows down. And so I can change the speed of my fluid by just changing the diameter of my tube. And so that's our first piece. Now, a good place, and this would be a good place to stop here actually because I got so many demonstrations to show you, was the brilliance of somebody named Bernoulli. And Bernoulli was looking at this and said, well, wait a minute. Didn't you just say it went faster? Sure. But then that means it has more kinetic energy. So where did that kinetic energy come from? What? Out of nowhere? I mean, what happens to this principle of conservation of energy? And so let's run through Bernoulli's thinking. And so maybe I'll take a little chunk of the fluid. Maybe I'll do this right here. And so I'll say, all right, let's look at that little chunk of fluid as it moves through the pipe. Now, again, you might say, okay, it's on a big surface area, a big cross-sectional area, and it's going kind of slow. But then, when all of this funnels down to here, it must, for the same volume, be much longer. And, of course, must be traveling much faster. So that basically this goes out at the same rate this comes in. But Bernoulli said, could you apply conservation of energy to this? And so let's look at the energy earlier on and then later on. Now, if you remember our principle of conservation of energy, it says this. It says the initial kinetic energy, let me call it kinetic energy 1, the potential energy, number 1, the work done by a non-conservative force, that would be like a friction. We're going to start using the word viscosity as the fluid rubs on itself and makes heat, would then equal to the kinetic energy at the other end plus the potential energy at the other end. In fact, let me even draw a new picture to this, because the picture I have here is really a picture of its speed changing. But Bernoulli is going to ask an even better question. What if it not only narrows, but it goes uphill? See, again, it's kind of the same thing. If it goes uphill, doesn't it gain gravitational potential energy? Where did it get it? So it goes faster, which gives it more kinetic energy, and it is higher up, so it has more gravitational potential energy. Where did that all come from? And so hopefully you'll see it here. Bernoulli starts off his thinking and says, well, let's ignore friction at first here. All right. So for today, and we'll run out of time to add viscosity into this mix, but that'll happen tomorrow. So let's just say there's no viscosity. There's no rubbing. There's no friction. So kind of an ideal fluid. All right. So let's start there. He says if you take the initial kinetic energy, so this little red blob right here, that's my initial kinetic energy. And then you take the initial gravitational potential energy. And here's kind of the magical step. Remember that elastic energy? Remember I was saying these don't squeeze much, but they do a little bit. Can you kind of imagine this is like a little spring, if you will? Now, maybe a little spring where the spring constant is so big that when you push even really hard on it, the spring barely moves, but there's still energy there. And it pushes back. Isn't that pressure? Isn't that what the pressure is doing? And that's where I want to go with this conversation. The answer to the question, where did the energy that lifted it up, where did the energy that speeded up come from? I would say comes from the stored energy in pressure. And so as it goes uphill, it's going to lose pressure. As it goes faster, it's going to lose pressure. It's going to get that extra energy from a force. That force is the pressure. Force times distance is the work. And so Bernoulli realizes that you could think about this equation right here as being the energy stored in pressure. And so I'll put it here like it's a spring, but this will be the last time I really think of it as a spring. This is just a way for I can tie fluids together with our mechanics. I'm just trying to say I'm going to think of this as some kind of pushing back, some kind of elastic energy here. And so more on that in just a second. But I'll have a 1/2 mv2 squared plus a mgy2 plus a 1/2 kx2 squared. Now, here's kind of an important question. Maybe we should look at pressure. Pressure was what? Force per area? Wouldn't that be newtons per square meter in units? And Bernoulli's thinking here is there might be another way to think about pressure. Instead of thinking of pressure as a force, multiply top and bottom by a meter. What would you get on the top? A joule. What would you get on the bottom? Cubic meter. So it's this magical step I want you to think about for pressure. Because again, we were introduced to pressure as a force per area in the last chapter. But there's another way of thinking about pressure. You could think of it as kind of a stored energy. Remember, energy comes from a push. Pressure is a push. All right, so this right here is how I want you to think about pressure as a energy per volume, kind of an energy density. Because that's how Bernoulli's going to do. What Bernoulli's going to do then is say, let's divide both sides of the equation by volume. And the main reason he wants to do that is this right here. Energy per volume is the pressure. Now, these other terms just become rho g y1. See, mass per volume, that's density. And this term just becomes 1/2 mv1 squared. Oh, sorry, not m. Mass per volume is density. In other words, instead of thinking about the whole energy, Bernoulli's thinking about an energy density. How much energy per volume? So this first term is the kinetic energy per volume. The next term is the gravitational potential energy per volume. And this term, I'll just call it the pressure energy, but you might even call it the elastic energy. Because if I do the same thing on the other side, this becomes a 1/2 rho V2 squared. This then becomes a rho G Y2, and this term becomes the pressure at point number 2. And so I'm hoping you see in this equation, which we call the Bernoulli's equation, that if you take all of the energy density you start with, it equals to the energy density you end with. So hopefully I'm not doing anything new here, but what I am trying to do is give an explanation then that if you had a pressure down here at pressure 1, and you were to ask this question, when it got up here to the top, where did it get the energy? Because it gained potential energy and gained kinetic energy. Where did it come from? I would say there's a lower pressure up at top. I would say that the reason it got up there and the reason it went faster is because the pressure here pushed it up here, and so there's less pressure here. And so we've given up some of our pressure energy and gained potential energy by gravity and kinetic energy. Yeah.
Could you think of it as it flowing from high to low?
Okay, now high to low sounds to me like you're saying it's getting
high pressure to low pressure.
Yeah. And so yes, I only hesitate there because to me that sounds like you're trying to overcome the friction or the viscosity, and we've kind of left that out of the equation. We're going to get to that. And so we're going to say, yes, there's always going to be a pressure drop because of the rubbing and the viscosity. So yes, it will always flow from high to low. But watch this for a moment. If I had taken a pipe and made it go downhill, I would say it flows downhill because of gravity, not because of pressure. And the pressure actually down there is higher. Because what happens here is if this is pressure 1 and it goes downhill to pressure 2, it's actually flowing towards higher pressure. I would answer it this way, that gravity actually wanted to make it speed up, but the higher pressure here resists it, and it actually flows the same rate through here. And in other words, it's changing its gravitational potential energy into pressure energy. It's not like a ball rolling down the hill where the ball changes its gravitational potential energy and changes it into kinetic energy. This is changing its gravitational into pressure. But then notice the flow is not from high to low pressure. And so it doesn't always flow from high to low because we have the effect of gravity here. And so it could actually be flowing to a higher pressure. Just that increase in pressure has to be less than the effect of gravity pulling it in that direction. All right, well, let me just rewrite this equation and look at it real quick, and we'll call it quits. But here is where we'll pick up tomorrow, and that is if you rearrange this equation, if you rearrange it so that you write it as P2 minus P1, that's the change in pressure. So imagine this over to here. You would say that is equal to 1/2 rho V1 squared minus V2 squared. And the other term would be rho G, and it looks like we would have Y1 minus Y2. And maybe you know what, maybe I should talk more about this equation just tomorrow. But I do want you to see then that the pressure here can either increase or decrease depending on how these energies increasing or decreasing. And so a change in kinetic energy or a change in its height corresponds to a change in its pressure. And so we're going to need to give this some thought as it flows through the pipe. Now I'll also say this is flowing without any friction. So more on that to come. All right. Well, we'll call quits for today. It's 5:10. Let's do the same as before. We'll start the lab at 11:10 or 15. We'll give you 11:15. Give you a little 20-minute break there, and we'll come back to chapter 12 tomorrow and go into chapter 13. And remembering the exam is only up to 11, so that's where you want to really focus your attention. Chapter 6, 7, 8, 9, 10, and 11. All right. We're on here. All right. Hey, welcome back. Let's go ahead and continue where we left off, which was on our fluid dynamics. And so we're looking at the physics of the fluids. But let me emphasize to both you guys here in person and you guys online that this chapter, chapter 12, is not on this upcoming exam. It'll be on the third exam, but it's not on this upcoming second exam. The original plan was to have it there, but since we kind of fell a chapter behind on the first one, and we're kind of catching up now because we're going to finish chapter 12. So I guess in theory we could say we'd catch up, but I didn't want to put that much on the exam. And this is a pretty significant chapter in the terms of the difficulty. So the fact that the test would be then chapters 6, 7, 8, 9, 6, 7, 8, 9, 10, and 11 is plenty of material to test on. And so I wanted to start there. All right, now let's go back to where we left off, because there's a lot of stuff in this chapter, but one of the biggest ones is Bernoulli's thinking. And so we left off, and I want to put it back here on the board. If we had a tube that had a cross-sectional area, say area 1, and the tube narrowed and went uphill so that now it is at a higher location and a smaller diameter, call it area 2. But also we could have, and we didn't get a chance to talk too much about that, but one of you asked a really good question, because it's kind of a gut thinking that where the water flows to, or the fluid flows to, is always higher pressure. And that's not necessarily true, because it's not just the pressure that's pushing things along, it could be the effect of gravity. And so if we called this then area 2 and this again area 1, we used the principle of conservation of energy and said then that if you had a little chunk here, call it like a disc, maybe like a quarter, moving through this pipe, and then of course it narrowed, so now it's going to be smaller and longer. I was pointing out that in this case, that same water is now going faster and it is up higher. So for both those reasons, it gained energy. And then where did it come from? And so pressure being a force over an area, if you multiply it by a distance traveled, you then get work or energy per volume. And so this was my way to introduce you to the thinking of pressure, a little bit different than the last chapter. In the last chapter, we thought of pressure as a force per area. Now we're going to think of it as like a little bundle of energy. It's another form of energy. And I was trying to give you an analogy of thinking of it like an elastic energy, that the molecules are kind of squished together. Now I want to be careful of saying that, because it's like a really, really large spring constant. That is, you barely push them in, so you could say, oh, they didn't really contract much, but it's an enormous amount of energy because it's 1/2 kx squared, and the k is a really, really big number. Anyways, we worked through this conservation of energy. It's worth repeating it here on the board, because if we ignore any friction, we could say this, that the kinetic energy that you start with plus the gravitational potential energy you start with plus the pressure, and that's kind of the new piece. And so we've done conservation of energy for our solids. And when we had solids, we thought of it as one solid piece. Now we change our thinking a little bit, and instead of thinking of it as one giant piece, we kind of replace mass with density, and so it's an energy concentration. But these are now three terms. And so back here where it starts, and let me label this 1. And so the fluid is starting at 1, and it has a kinetic energy and a gravitational potential energy and what we'll call a pressure energy. Or maybe I'll just call it an elastic energy. And then as it stretches out, it becomes, or maybe changes, I don't really know, it could gain speed, as trying to indicate here, if it narrows, it will gain a speed. Then it could gain in height, or actually lose in height also, and which means the pressure would change, either increasing or decreasing, the pressure making up for the energy changes. And so there's another set of energies here is what I'm getting at. And of course, we finished off with the equation writing it this way. I said, let's take the position number 2, so over here is position 2 where it goes to. If we write this as pressure 2 minus pressure 1, so what is the change in pressure as it goes from one place to another, you will hopefully see that there are 2 reasons. One of them is that the kinetic energy changed, and so I'll put these 2 terms together. But another reason is that the gravitational energy changed. And so then it kind of fits our principle of conservation of energy. We're saying this increase or decrease in pressure, so the change in the pressure energy, is a result of when it changed its gravitational or its kinetic. Now, in this first drawing I have, where the fluid goes uphill, you can see that y2 is now greater than y1, and so this term is negative. So that would tell you it's a pressure drop. That would tell you the fact that it goes uphill, that alone is a pressure drop. And it makes sense, because it's getting the energy to go uphill from the change in pressure. Likewise, in this picture, since my tube narrows, it'll go faster at point number 2 than number 1. And so if we look at the kinetic energy here, velocity number 2 is faster than number 1. So again, this would be a negative. It's another reason for a pressure drop. And so I would say that there are 2 reasons why the pressure is lower at number 2, and that is because we had to give up that energy. Some of it went to lifting it up with gravitational potential energy, and some of it went to making it go faster. Now, it gets more complicated when those 2 are kind of fighting each other, but the way this one shows, I would say lower pressure at 2 than number 1 for 2 reasons. And then likewise, this one is where it might get a little more challenging to decide if the pressure is greater at point number 2 than point number 1. Because as the fluid starts here, and so I'll take this chunk of fluid, maybe like a quarter, and it flows through, it now gets elongated, and so it is now spread out. But notice, because the pipe narrows, it goes faster, it gains kinetic energy. And so this right here would tell me, oh, there should be a decrease in pressure. However, also notice that it went downhill. And that means that y1 is greater than y2, and so that's an increase in pressure. And so the whole net effect of whether the pressure at number 2 is greater than number 1, I can't really tell unless we had some numbers to work with, because we got competing factors. And so I wanted to kind of point that out. It's not necessary that point 2 has a lower pressure than point number 1. Because it could go, in this case, downhill. But it could also just spread out into a wider pipe, and then a wider pipe would go slower, and so there would be an increase in pressure because we're losing kinetic energy, and it goes somewhere. It goes into storing it as a pressure. And so that's what I really wanted to emphasize. Now, I also want to just take a moment here before I kind of demonstrate Bernoulli's principle here, is that, did you notice the way I defined 1 and 2? Did you notice we started at 1 and went to 2? There's nothing magical about calling it 1 or a 2, but I do want to point it out because I got a little confused when I was reading your author, and I was like, wait a minute. Because I'll show you, at the end of the chapter, he changes what he means by 1 and 2. So I want to point that out to you. So hopefully you won't get confused like I got confused. I go, wait a minute, something seems backwards about this. And so I just want to point it out again. Notice at this discussion, and I'll call the first half of the chapter, he says where it starts at is 1 and where it goes to is 2. And he's going to change that in the second half. So don't be too confused. We just got to kind of reverse what he's doing if we want to kind of match it with the first half. So to match the first half of the chapter with the second half, that's just kind of my warning here, and I'll show you in a picture in just a second here. Now, here's what I really want to focus on, is this term right here. If you just had a fluid at the same level, so it doesn't go uphill or downhill, this would be 0. And so let me put a special case. What if y1 equals y2? So there is no uphill or downhill. And by the way, maybe I'll pause, because I would say this term is really what we talked about last chapter. Do you remember how we said pressure increased with depth? Maybe I'll put it over here on the side. Didn't we say the pressure was equal to rho GH? And so if you were at some level and went deeper in the fluid, even if the fluid wasn't moving, so in other words, if you put 0 here and 0 here, non-moving fluids, you would get a difference in pressure at the different heights. And that's exactly what this is saying. And so I would say we've already covered the case where the fluid is not moving and it just goes up and down. So I want to focus our attention on one that I think is a little surprising, and that is when it changes its speed. And so if we have the heights the same, then you can have a pressure change, either positive or negative, depending, of course, on if the speed changed. And so let me show you a few examples of this. This is really often referred to as the Bernoulli's principle, and basically it is saying that where the speed is high, the pressure is low. Makes sense, right? Because where the speed is high, isn't that where the kinetic energy is? And where did it get that its kinetic energy? From the loss of pressure. And so your author gives a couple of examples. I'll try to do some real life examples here, but he says, look at maybe 2 vehicles traveling down the road. And the bigger they are, the more noticeable this is. Have you ever been driving, and this is kind of what he's working with, trying to tie it to your real life experience. Have you ever been driving down the road and maybe you have to pass a truck? And as you pass it, it feels like you're being sucked into the truck. Yeah, this is a good example of a Bernoulli's principle. See, what ends up happening is this car, maybe I'll take the car back here, the air flows around it on each side. And then I would say then that the air on this side does have a drop in pressure because it has a velocity, but it's the same drop in pressure on the other side because it's the same velocity of air. And if you have the same pressure left and right, well, the air would push you equally to the right and equally to the left. You wouldn't even notice it. So most of us, as we drive down the road and there's no other cars around, we're just driving down the road. The fact that the wind is blowing just gives us a lower pressure. It's not so much that we notice, and the best thing about it is it drops equally on both sides. And so we don't think about it. We just say, okay, the car's being pushed by the air. And then over here, the car's being pushed by the air. But they're equal, and so we don't feel any effect. But if another object gets near you, and in this case a truck, a big truck, it kind of funnels all this air into a narrow spot, and the air's got to go faster through that little narrow spot than on the other side. And so if this is me driving the car, the air over here on my right, near the truck, has to go fast. That means its pressure is low compared to the other side. And so this pressure is greater than this pressure. So the net effect is the car gets pushed into the truck. And so that's why you're like, whoa, 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 and you want to make sure you're using the wheels and the friction of the wheels to keep you away from getting pushed into the truck. And so it's not just psychological. You really are getting pushed into that truck. And so this is the idea of the Bernoulli's principle. Watch, let's see if I can illustrate it a little better. I got a couple of little silly ones here. Here's kind of my favorite one. It's just really low tech. It's a piece of paper folded to kind of look like a bridge, if you will. And I would say right now there is air on top pushing down, but there is air underneath pushing up. And they're equal. And when they're equal, we kind of forget about it. But what if one of them was moving? What if it was flowing? Well, then its pressure would drop. So I'm going to use this straw, and I'm going to blow air underneath. Do you see what happened? Wait. Do you see how it collapsed down? I mean, it almost looked like I was shooting air at it. It almost looked like I was doing this, right? And I would say kind of indirectly I am, because what I'm doing is I'm lowering the pressure here. Right? The low pressure is where the high speed is. See, the high speed is the high kinetic energy, and it gets that high kinetic energy from the reduction of the pressure. And so by blowing under here, the pressure in here goes down, and the pressure up here is still the same, and since they're not equal, it squishes it down. It's another just as simple, but I think very effective one, is to say, what if I just take a piece of paper and I kind of hold it here like this, and of course it arcs over because gravity, right? Gravity pulls it down. There's a weight pulling it down. But if I also look at the air pressure, I would say, well, there's air pressure here and there's air pressure here, but they're equal, and so they don't really have a net effect on it. But what if I made the air to start to move, maybe on this side? Wouldn't that lower the pressure? And so over here the pressure's higher than over here, and that would then lift the paper. And so if I just kind of hold it and blow across the top, see, it almost looks like I'm doing this, and I'm hitting it. I didn't do that, right? What lifted it up was actually these air molecules under here. These are the ones that lifted up. All I really did was reduce these pushing down so that the ones pushing up, they were already there. And so it's not that I'm pushing up, it's that I'm reducing the ones pushing it down. See that subtle difference? So, and it just kind of lifts it up. I think this is kind of a fun one. This one is back to kind of this car. What if I would take some air and an object? The air kind of goes up and around. And I guess it goes equal on both sides. So it's kind of trapped in there. But it's kind of noisy, so I'll turn it off here for a second. What if I were to hit the ball so that it went partly out of the flow right here? See, See, because it's partly out of the flow, the air's not going to go around over here to my right side of it. It's all going to be over here on my left side. And that's the low pressure. So what will it do to this big beach ball? It'll push it back in, because remember, this side is where the air is not moving. This is the high pressure. And so as I try to push it out, the air pressure pushes it back in. And when it goes too far this way, then over here on the right would be the low pressure, and over here on the left would be high pressure, and push it back in. And so this is actually a very stable and interesting effect as we turn it on here and try to just catch it. Da, 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 da. Good luck getting it out. It's hard to get it out. It will fall. Whoops. I say it's hard, and there we go. But it will follow it, and I can move it over to here, and I can move it over to here. And it's just kind of stuck in this flow. Now, obviously, if I hit it hard enough, I can push it out. But there's a significant amount of force from these little molecules, and so by making them go faster, I can have that effect. In fact, that leads me to kind of another fun little one here, is how does an airplane work? And there's a lot going on in an airplane wing, so I won't say this is the full effect of how an airplane flies. But if you take a little cross-section of an airplane wing, the air flows up, and the arc over the top makes the air flow a little faster. It's got to kind of cover a bigger path than the air underneath. Or you might even say the air underneath gets trapped a little bit and moves along. But either way, the movement of the air is faster above the wing than below the wing. And so what would that say about our pressure? Where would the low pressure be? On top. And so if you have a low pressure on top and a high pressure underneath, isn't that a net upward lift? And so this is how the airplane flies. And so as much as it was quite impressive to see that beach ball trapped in here, I think it's much more impressive that when you have a couple of ton 747 able to lift off the ground and fly because of the pressure difference, that's where you really see the effect. And of course, they also talk about a sailboat also, so the same basic principle. It's really a wing. You have a little arc to it. And you're trying to force the wind to blow on the curved side so that it blows a little bit faster than, I'll call this the convex side, and a little slower on the concave side. And because of that, you have a low pressure on the convex side, and then that pushes it along, or you might even say pulls it along through the water. And so there's your sailboat. All right, it's why I brought this one out. This one's kind of a fun one to see. In fact, this one uses air, and it's kind of hard to see the air moving, so I got kind of a low-tech one that uses water here. But if you look here, there's a rubber hose, there's some tubing, and you'll notice this tubing, as well as this tubing, changes its diameter. It starts with a big wide tube, then narrows. And so this one narrows here, and this one narrows here. And as we said earlier, if it narrows, it's got to go faster. And as we're trying to say now, if it goes faster, it has more kinetic energy. And if it has more kinetic energy, it must have gotten that from the pressure, so there must be a pressure drop. And so if you look at this, there is some blue liquid. And notice our conversation from the last chapter, the same level. That's because down here the pressures would be the same. And so as you go up, they're both open to the air right here. And so right above the liquid is air pressure, and then plus distance, so they're equal. But if they didn't have the same air pressure here, then the heights wouldn't be the same. In other words, if we somehow lowered the pressure in this middle one, wouldn't the height of this column be higher than this one? That was our discussion on, millimeters of mercury, how that worked. So let's see what happens if I just blow through here. If I blow through here, I would think it would go really fast right here, which I would think would be a low pressure. And then a low pressure should then make this one up higher. Well, let's see. Sure enough. See how high that one came up compared to that one? And even compared to that one. You'll notice it flared back out. And so the kinetic energy went down, which means the pressure went back up. It's kind of fun to see it with this one because I can combine this idea of a Venturi tube where I change the speed with that beach ball effect, but I will do it with ping pong balls. And so you'll see little openings here. This is to measure the pressure. But instead of measuring the pressure with either a pressure gauge or with the water going up, I'll just see how high does it lift a ping pong ball. So it's trapped in that flow, and it's pushing the ping pong ball up pretty high. So I'd say there's probably a pretty good amount of pressure right here. Notice how much lower it is, which tells me there's a lower pressure in that narrow part of the tube because it's going faster. And then it widens up again. So it slows down, which means the pressure goes up. And so it goes back up. Now you'll also notice it doesn't go up as high as this one. Well, that's what's going to come next because we have friction also. And we're going to lose energy to heat. Excuse me. So we will have to talk about the next step, which is a loss of energy due to the heat. But as I said, right now, we'll just talk about a fluid that would be flowing without any resistance. That is interesting enough, and that's really what I'm after. Well, I don't know if I should keep going with this. I do have a kind of another fun one. Maybe I will show you this one. But there's a lot of really good examples of a Bernoulli's principle here, and a spinning object is a good one here. Here, you'll see that I have this cylinder that I can spin. And it is on a track that has pretty low friction. And so it can move pretty easily left and right. But if you like any kind of sports, tennis, baseball, golf, the spinning of the ball traveling through the air has a very interesting effect because it can change the direction the air is flowing. I'll take a baseball here. What if I were to hit the baseball so the bat comes down at an angle, and as it takes off, it has what we'll call a backspin? Kind of the same idea of a four-seam fastball. If I grab these four seams and I throw the ball, and as I release it, it has this backspin. What happens to the air as the ball is spinning? See how the threads in the baseball, and see how they're lined up, so all four of them are kind of like grabbing the air like little scoops, and they're trying to lift up the air and dump it over the top. So the air doesn't flow equally over the top or under the bottom. It goes more over the top. So where's the high speed? The top. What does that say about the pressure? Low. So what happens to this ball? Yeah, it has a net upward lift. And so if you're standing at the plate and somebody's pitching this to you, you go, oh, here it comes, and you go to swing and the ball lifts up, goes over the bat. Strike one. You missed it. Or the pitcher curves it the other way. Or maybe I'll do a curveball, and so they come over the top. And it's spinning like this. What would this do to the ball? Yeah, make it drop down. because the high speed would be underneath. That would be the low pressure. So again, you're waiting for that to come, and then all of a sudden you go, and it just kind of falls out underneath the bat, and you miss it. And it really doesn't matter what sport you like. Tennis is the same idea. If you want to beat your opponent, you're like, okay, they're on that side of the court. I'm going to hit it over to that side of the court. And I want to hit it fast enough so they can't get to it. But I can't hit it too fast because it'll go out of the court. It's got to land in the court. So how can I hit it fast, go over the net, and then fall into the court? So I'll hit it, and my follow-through will roll over the top, just like that curveball we talked about. And it'll have what we call a top spin. And the top spin will then make the air go fast underneath. So it'll go really fast. And if it wasn't for the spin, it would have gone outside of the court. But the spin then will help it drop down, bounce in the court, go out, and my opponent can't get to it fast enough. Or if I'm doing a serve, maybe as I throw it up, and I'm going maybe to the ad court here, and I slice the hit. So as it is going in this direction, it is spinning this way. What would happen to a ball that is spinning like this? Where would be the high speed? And it would drag the air over here to my right side. And so that'd be the low pressure. And so as this ball goes, it comes across, and it's going to then head out further away, making it harder for my opponent to get to it. Or even if they're lucky enough to get to it, now they're way over there, and so my return of their return is over there, and then they can't get to it. And so the spinning of it plays a role. Golf ball, certain number of dimples, size of dimples. Baseball, size of threads, number of threads. Tennis ball, amount of fuzz. All of those are well dictated in the game because that's what grabs the air. That's what scoops it around. And so if you had a golf ball that had too many or too big dimples, it would fly better. To be honest, that's how I play golf. I buy the long flight ones. It makes me look good. They're not legal, but they work really great. I just take my club, I hit it, they have a little backspin on them, they grab more air, and they just, and all of a sudden, wow, my 125-yard shot's now going 200 yards. I look like a champ out there, right? And it really can make a difference. Now, if you mess up, though, and you do a slice and you spin it sideways, ooh, now it makes your slices much worse. Because it was just going to go a little bit out of the fairway. Now it's spinning this way, and it goes out of the whole golf course. And so it all depends on it. In fact, this beach ball, I think you can see it really well. Here's the backspin. What if I hit it kind of towards you guys, okay? You guys brave enough to catch it here? And so I'm going to hit it, but I'm going to give it a backspin. So I'm going to do something like this. And watch it. It will rise up a little bit. And then gravity will take it down. And it just flies different. And so, like that. Perfect, thank you. All right. Now, what if I did this? What if I hit it with a slice? And so as I hit it, it'll go forward at first. But with a spin this way, it'll begin to curve out to you. All right. And so, sure enough, it started that way, and then it spun. Thank you. But what if I do it the other direction? What if I throw it up and I spin it this way? And so it's spinning here. It'll go towards you guys. All right, hands up here, okay? So, and so it'll curve that way. Well, I'll do the last one. It's not too exciting and kind of hard to see. But if I give it a top spin, it just kind of goes, whoop, and it just kind of sinks down. And to do that well, I'll kind of have to hit it like that. So maybe I'll hit it up towards that light right here. And so watch it. It'll start towards that light, but it'll quickly fall down into the court if this was a tennis ball. Nope. And there kind of angles down. Well, you get the idea. Let me get back to my little demonstration. So here's kind of the fun one. If I were to not spin this, take a little air, blow it on the cylinder, I would say the air flows equally on the left and the right. And because it flows equally left and right, there's a drop in pressure of the same amount, and there's not a difference. And so this doesn't go anywhere. But if I have it spinning, so if I pull this string, so notice when I pull the string, it's going to spin this way. And so if I blow the fan here, the spinning of this cylinder will force the air, I guess, to my left. And so over here should be a lower pressure than over here. And then that should make it move in this direction. All right, let me give it a try. So there's the spin. There's the air. I put it on the cylinder. And sure enough, see it again? And if I were to get on the other side, again, spinning this way, the air is going to go fast on this side when I put it over here. Making low pressure here, making it go that way. And so sure enough, the air pressure pushes around. And so the amount of spin is an important piece in all that. Well, like I said, these are kind of fun ones to do, maybe more fun for me than for you. But it's nice then to really see the speed come into play. And that's our fluids in motion, our fluid dynamics here. All right, well, we need to continue on because as I said, there is resistance going on. And so let's throw that into the mix because everything we've done so far, I've really been saying, well, this is without any resistance. And we use a special word when we're using resistance of fluids because they rub not just on the outside of the pipe themselves, and that's kind of minor, they rub on themselves. That is, the water flows and one part of the water flows faster than the other, and so there is a rubbing effect. And that, of course, impedes its motion, and so we call that a viscosity. And so the new word here is viscosity. I'm going to put here in parentheses friction, but I must say we really save the word friction for solids rubbing on solids. But I think this will help you. Since we already did the mechanics of solids, then let's talk about then the fluid rubbing on itself. And there is a Greek letter eta that we like to use to kind of describe how much resistance an object actually has. And in fact, your author has some really good pictures here. Let me come down here and look at picture, I wrote 13 here to kind of give you an idea. If you just had water flowing in a pipe or air flowing in a pipe, whatever you want to call it, they would all flow, unhindered. They would flow equally. But because of viscosity, the fluid near the edge of the pipe right here would kind of grab on, would kind of hold. And so on the edge of the pipe, the fluid would go slow. But in the middle of the pipe, it would go the fastest. And so there would be these boundary layers. In fact, figure 12 shows a little experiment that is used to figure out how well a fluid flows. A way to measure its viscosity. And you simply take this. You take two metal plates, or doesn't have to be metal, but two plates, and this bottom one is locked into place. And so it's kind of like my hand on top of this surface. where the table's locked into place. But if I put a little liquid between my hand and I pull it, how well does it slide over that surface? And so we can measure then, how well does the fluid flow? See, what happens would be something like this. If you kind of think of that fluid as being levels, and the total stack is L, and you, excuse me, you push with a force F, you can push with a force F so that this top plate moves at a constant speed. How much force you are applying must be connected then to this viscosity. I like to think of it this way, that what I'm doing to push that top plate would be a force from my hand times L. That would be like the lever arm. That would be the torque. You could kind of imagine, like we've seen in the past chapters, that this would be easier to move if we had a thicker fluid to it. See, what I want to know is the effect just from the fluid, not just how thick the fluid is. So I'm going to try to find a factor that opposes the flow, that has only to do with the fluid, not other factors. So I want to make sure I understand the other factors, because I would say then what's helping me getting it flowing is not just the force from my hand, but the leverage I have. And then I would say what's stopping it from flowing, and I'll just put here the amount of mass that I'm moving. Now, the reason that is important is because the other factor is what I'm going to call the viscosity. So I'll say it again. What I kind of want to get here is the factor that has to do just with the intermolecular motion, and I would call it the resistance to it flowing. And so these two factors make it flow. These two factors oppose it. I really want to know this factor. In other words, I'm not real interested in how much flows, although I do want to say this. You could imagine that if this plate had a bigger surface area, as you pull it along, wouldn't you be pulling more mass, and wouldn't it be harder to move just because it has more mass? And so that factor, just that it has more mass, is going to be in here. I don't want it to be part of my viscosity. So here I'm going to put the symbol eta for the viscosity. And then over here, I'm going to put any of the factors, and there's two of them here, that to determine how much mass I'm carrying along. And I would say that the amount of mass would be related to this surface area, because that's what's in contact here, and then dragging all this along. But I would also say it has to do with how fast I'm pulling it. And so right here, I'm going to say times V times A. And what I'm after, and this is the part that I was saying yesterday, that I'm kind of impressed that your author would go down this road and try to give you viscosity. It's a tough concept. And as a first beginning class, a lot of times we kind of skim over this and say, well, maybe we should talk about viscosity next semester. However, I appreciate what your author's doing, and I want to follow that. Your author's trying to say, no, this is an important piece of the physical world needed in the biological sciences. And you guys aren't going to be having another semester of physics and fluid dynamics and stuff. And so let's do our best to try to get the students to understand it, even if that means kind of doing some hand waving with some of the equations, so at least they can see how this physics is applied to the biological world. And so this is kind of my hand waving, that I would say that this number eta, called the viscosity, you want to think of it as just how difficult it is for the fluid to flow. And when you go to actually measure it, then you would have to then factor out things like the mass and say, well, it's hard to move because it's got a lot of mass. That's not the part that eta is supposed to represent. Eta is supposed to be a number just how hard is the fluid to move, period, regardless of whether you have a lot or a little. Yeah.
To go back to the example that you were talking about earlier about the pipe and the water flowing. So if there's greater pressure in the middle, then what would allow it to move faster in the middle? Would it be the water going slower because of the pressure from the pipe?
So if the pipe narrowed, like this one here, and now it goes faster?
It's not a constant shape. It changes size and diameter, is that why?
Yeah, yeah.
Oh, okay. I thought it was all just...
Yeah, I didn't say it today, but yesterday, you might remember we had what we called the continuity equation. We said if you had a pipe that had an area 1 and it was moving with a velocity 1, to get the same amount of mass through there, and you change the area, you have to change the speed. And so, looking at this math, if this area goes down, then this speed has to go up.
Okay, that makes sense about the area stays the same.
Yeah. So in this case, that's why I said this one went faster, because the pipe narrowed. And then when it got here, the pipe got bigger, so I said it slowed down, which then the ping pong ball went higher. Yeah. Okay, so I'm going to go ahead and do my best to try to say, okay, this is going to be our equation for measuring eta, if you will, the viscosity. And hopefully it gives you an understanding conceptually about what this is. You can kind of see the units here. The units would be this. You would have force in newtons, you would have length in meters, you would have speed in meters per second, and you would have area in square meters. And you can see that one of the meters cancels off. And then you have a Newton per square meter. That's a Pascal. And then you have the seconds, which is in the denominator of the denominator. And so we will measure our viscosity as Pascal times a second. And again, it's a measurement of how easy or how not so easy is the fluid flowing. And I think your author then uses some experimental data. There's a table somewhere, here it is, that says, all right, how well do these things flow? And it's a big table, covers a couple of pages here. Maybe I'll pause right there because we could look at the water. And they give two different temperatures, but then there is the viscosity. This is an indication of how well or not so well does it flow. And most of the time you can see right here that for the higher temperature, because the molecules are bouncing around with a little more bump and spread to them, they flow easier at the higher temperatures. And so at a cold temperature we have this viscosity, and at a higher temperature we have a little lower viscosity. I think on the next table, yeah, they continue on with water, and you'll notice that as the temperature keeps going up, and 37 is kind of the one I wanted to point out for you guys, right? That's human body temperature right there, 37. And so this is the viscosity of water. And then blood. Here is blood at 37 degrees, and this is the viscosity. And at room temperature, it, of course, has changed. Okay, and so it's a little harder to flow. We got blood plasma, and different alcohol. We got ethanol alcohol, methanol alcohol. We've got different oils and blah, blah, blah. Maple syrup. In fact, maple syrup is kind of the standard example. You ever heard the phrase, you're as slow as maple syrup in January? What does that mean? Well, maple syrup does not flow very fast. It's got a very high viscosity. And so it's a good indication of what we mean by high viscosity. You pour that syrup and it slowly oozes out. It's nothing like pouring a pitcher of water. That's the best indication of what we mean here by viscosity. How well does it flow? But the maple syrup does flow. I mean, you will get it to get on your pancakes, and then you'll get a pile, and it will run off, but it'll take a while. It slows very slowly. And if it's cold maple syrup, so if you're as slow as maple syrup in January, and I know here in Santa Barbara, in January is probably even warmer than August, so that's not a good comparison. But in New England, when you say you're as slow as maple syrup in January, you mean it's maple syrup that's cold. Meaning it might take 20 minutes for this pile of maple syrup to flow off of your pancakes. And so there's the idea. And some of the numbers that go with the viscosity. Now, without proof, like I said, I've got to admire your author here. Your author says that then if you were trying to move water or any fluid down a pipe, and here's the conditions, same size diameter, so I'm not going to change the diameter here, and it's round in cross section, and so that most of the cases, that certainly would be a good example of maybe blood flowing through a vein or an artery, okay? There is going to be, if we start here at number 1, and we say there's a pressure here, and we go to number 2, and so we say there's a pressure 2, there is going to be a loss in pressure energy because it goes to the heat of rubbing. Remember our conservation of energy? Remember how we did Bernoulli's principle and I said let's just forget about heat energy? Now if we throw that back into the mix, we will say that we're going to lose pressure energy in this case. I deliberately picked a pipe that, notice, it's the same diameter, so does the speed change? No. I deliberately made it horizontal so it's not going uphill or downhill. So does the gravitational potential energy change? No. So if there is a loss in pressure energy, it's not going to kinetic, it's not going to gravitational, it's going to heat energy. This is the viscosity, and so it would warm up. And so without proof, your author gives you a nice little equation here, although I'm going to write mine a little different. I'm going to put the 8 eta L on the other side. So if this pipe has a radius of r and a length of L, 8 eta L times the flow rate, and is it, yeah, pi to the 4 power, and I'm going to put a negative in front of my equation. Put a box around this. And so I'm just going to say, we'll see some homework problems like this. We'll talk about blood flowing through the human body or something, and we'll see that there is a loss, so that's why I'm going to put a negative, a loss in pressure, and so pressure 2 is lower than pressure 1, and the reason for that is we had to give up some of our energy to overcome the rubbing and the friction, the viscosity. The blood or water that's flowing in this pipe is now a little bit warmer. And in fact, this reminds me of what I said earlier. You might notice that he puts the flow rate by itself. I like to put the pressure by itself, so I'm writing it a little bit different. But you'll also notice I put a negative and your author did not. That's what I was commenting earlier. He comes over to here, and he's in his discussion, he's saying the water starts over here at the water company and is delivered to the houses, and so notice he calls number 2 where it's delivered. And this is what I was kind of my warning that kind of threw me when I first read that. Wait. Shouldn't, I saw that equation and I said, shouldn't there be a negative here? He's got it backwards, and he only got it backwards because he changed what he's thinking as number 1 and number 2. So that was kind of my warning. So I'm not going to follow your author. I think that's a mistake right there to switch that in the middle of the chapter. So I'm going to leave number 1 as where we start, and number 2 is where it goes. And that way there'll be a negative, there'll be a drop in pressure. And you can see it really depends, of course, on the viscosity, but notice how long the pipe is. And that kind of makes sense. This one's not a surprise. And this one's not a surprise. This is how much you're flowing. And the fact that the radius is in it is not a surprise. If you had a small radius, you would kind of go, oh yeah, small radius, hard to get through. But here's a big surprise to me. What if you cut the radius in half? So what if you went from a 1-inch pipe, and so maybe you're putting in a sprinkler system, and you dig up the front yard and you hook up to your water meter and you got a 1-inch line, and you decide, well, I'm going to then save a little money when I go to Home Depot, and I'm going to hook a 1/2-inch line. But I don't need a full 1-inch line. I mean, I'm just going to water a few plants here. Okay. And you go to a 1/2 inch. Well, I guess I don't need both of those. But you go to a 1/2 inch line. You cut the radius in half, right? But look how much harder it is to get it to flow. Or put another way, look how much the pressure will drop as it goes through that. It is radius to the 4th power. So if you take a 1/2 and you raise it to a power of 4, that is 1/2 times 1/2 times 1/2 times 1/2. That is 1/4 times 1/4. That is 1/16. It's 16 times loss of water pressure trying to get through that narrow line, that 1/2 inch line. It's an amazing difference in what it can make here. And that really is probably the best thing to kind of get out of this whole discussion on viscosity, is that viscosity is its resistance. There's going to be a loss in pressure, and it's highly dependent on the radius. The length and the amount usually doesn't surprise people, but the radius and, of course, the material does. And so that's what I want to emphasize. Yeah.
Wait, so that R is raised to the 4 or not?
Oh, I'm sorry, I didn't write that real well. Yeah, it's a power of 4. Your author, I hope, did it a little better than mine. Where was his equation? Yeah, so right here on his equation, yeah, it looks better. Yeah, so it's raised to a power of 4. All right, yeah. Good catch, good call there. And so, like I said, kind of a neat one. In fact, I thought before we left viscosity, we would come back to that same picture that we kind of were looking at. Remember, in the last chapter, I said, hey, that last section, I would encourage you guys to read it. It's not really testable material, but it talks about all the different pressures in the body. Now it might make sense. I mean, watch this. We would have a pressure coming out of the right side of the heart here, or is this the left? I guess the heart would be here, so it'd be left when it's in the body. Okay, so left side of the heart, and it is 120 millimeters of mercury. And see, as it flows through the arteries here, it's going to lose pressure. That's what I'm talking about here. There is going to be a drop in pressure based on the viscosity of the blood, which, as you saw on the chart, would depend on the temperature and, of course, how long they are and the size of them. But what this one is trying to say here is there would be a drop, it looks like, from 120 in this picture to 85. 20, what is that, 30? 35? So we got a loss of 35 millimeters of mercury as we just get to the place where they start to spread out and do the things that the blood's supposed to do and feed the muscles and all the other things. And of course, the pressure continues to drop all the way through the whole process. But we need enough pressure then to make the flow throughout the body. All right, well, like I said, that's a pretty advanced topic. And the math, fortunately, the end result, notice I didn't prove this to you, but the end result's just some algebra. And so I think that's why your author says, all right, let's just use the end result, and this will be useful for the students studying life science without going into the engineering of why this comes out to be. But your author then even goes a step further by saying that, hey, what we've been talking about really so far in our fluid dynamics is what we call a laminar flow. And sometimes the flow is much more complicated. It's what we call a turbulent flow. Maybe a picture is helpful here, because the pictures I was showing you earlier looked kind of like the first half of this picture. That is, if you could then see the fluid flowing on a microscopic level, there would be what we call these streamlines. That is, this molecule here and this molecule here would be flowing in the same line. And even if they were going at different speeds, they would at least follow these lines. They wouldn't cross over and intermingle. So that's called a laminar flow. And really that's the best flow if your goal is to flow. So if your goal is to move blood from the heart to the lungs or from the heart to the legs, then the best way to flow it is with a laminar flow. But if you get going too fast, or if the viscosity is too much, what will happen is they'll drag on each other and they'll kind of swirl around. And instead of moving down the pipe, they get all crazy, and that's called turbulence. And this is what the author's trying to show here, that maybe back here we have a laminar flow, and then the tube narrows, and maybe plaque or something here, and so the plaque is built up on the artery walls. And so as the blood tries to flow through there, because it's narrow, it's got to pick up speed. Okay? And it's, maybe I should pause right there. This is, of course, means to get the blood through there, the heart has to have a higher pressure. And so we call that high blood pressure. That, oh, you're in danger. You have high blood pressure. Why do you have high blood pressure? Perhaps it is buildup of plaque. Your heart is working harder to get through those narrow spots, which, of course, after a lifetime of high blood pressure can lead to all kinds of problems, including heart failure here. And so plaque can be obviously a significant health issue here. In this case, though, it is actually a problem, because now it narrows and you create this vortices in here. And the fluid is just crazy. And to calculate how hard it is for the fluid to go through is really extremely difficult. And so we're not even going to try to attempt that. Well, I'm just going to try to attempt to say, if you get turbulent flow, it's difficult to move it through. And so if your goal is to get the blood flowing through the body, you don't want it to be turbulent. However, if you want it to mix, you do want it turbulent. So there's a flip side. If you're an engineer and you're building a carburetor or a fuel injection system, when you inject that vapor of gasoline, or starts off as liquid, you want a turbulent flow going into the combustion chamber. So you'll eject it really fast, and you want it to spin and swirl and the gas to evaporate and mix with the air and get ready for igniting it. And so there are different reasons you may want or not want turbulence. And like I said, mixing things, you want turbulence. But delivering things from one place to another, you don't want it. So if you're the water engineer for the city, you don't want the turbulence in your pipe. You want a laminar flow. If you're a human trying to get blood from your heart to your muscles, you want a laminar flow. If you're an engineer trying to mix gasoline and oxygen together in order to convert them, you want a turbulent flow. So like I said, there's goods and bads up here, but The turbulent flow, just what it is what I wanted to take a moment to discuss here. And in fact, your author does a good job, I think, in this picture and saying, okay, what if, and he just gives a spherical object trying to move through the air and says, all right, maybe I'll think of this as a baseball again. And so a baseball going through the air, if it goes slow enough, the air just kind of separates as it moves through, or you can think of it the other way around. The object is here and the air just kind of goes over the top or under the bottom. There's no mixing, there's no swirling going on, and it actually moves through very easily that way. But if you get it going too fast, then maybe on this back edge, and they're trying to show right here, that it's fine at first, it's laminar, and then over here it gets all turbulent. And the faster it goes, the sooner this turbulence begins. And so as this thing goes through, we would say there is a place where it's all laminate flow. There's a transitional place. And then there's a place where all around it is turbulence. And that turbulence is just going to make this really hard to get through. And so if you're an engineer trying to build an energy efficient car, you'll probably design it in some kind of shape and aerodynamics so you can get a laminar flow of the air around it. On the other hand, if you're an engineer and you're trying to build a vehicle, we'll call it a semi-tractor trailer, that all you want to do is load a lot of equipment in there and move it from the port to the warehouse. Your interest is more about the volume in there, not the shape, and because of that, you probably get a lot of turbulent flow, and because of that, you probably get low fuel economy. And so, you know, what's your goal? What are you shooting for here? My point here is turbulence is really chaotic and takes a lot of force and a lot of energy to move through. So what I'm going to give you is a result of a lot of numbers. We call this Reynolds number because it was named after something Reynolds, I forget his first name. But the great scientists working in that field realized that if you took the viscosity, right, that's really saying how thick the material is, and you compare that to the density, how fast it's going, what size of a pipe is it in. This is referred to as the Reynolds number. And so if you have a Reynolds number that is less than about 2,000, the air becomes very streamlined and is what we call laminar flow. However, if this number is greater than 3,000, you're going to have all kinds of little swirls, mixing of the fluid, which you may or may not want. Like I said, there's reasons you might want turbulence and reasons you might not want turbulence. But I'm thinking for you life science, you probably don't want the turbulence. You're trying to deliver blood through the body. And so you get this very turbulent effect here. Yeah.
What if it's like 2,500?
Oh, and so in between is kind of this picture where you get turbulence on part of the object, but not the whole object. Actually, I shouldn't even have said an object. This is just with the water flowing itself, so it doesn't have an object in there. So that was a bad answer. So let me try my answer better here. So if it's somewhere in between, you might get something like this. So the water's flowing in a laminate, and then all of a sudden it goes turbulence, and then goes back to laminates, and then goes turbulence. And so it maybe oscillates back and forth. Or maybe throughout the pipe, this side says turbulence, and these are laminates. So you're in a transition zone. And so that's why we kind of give this range of numbers. Yeah.
And does drag occur at that point, or is that just when it's super turbulent?
So So let me say there'll always be some resistance. There's still viscosity. So when we're doing a laminate flow, which what I was talking about a moment ago, and I said this right here, this is a drop of pressure. This is what you might call a, what was the word you used, drag? Okay. And I want to kind of stay away from that because drag applies a solid object moving through the fluid. And I'm trying to say here at the viscosity, this is just a fluid flowing by itself. I'm not talking about the object in the fluid trying to move through. I'm just talking about the fluid itself. So I don't want to use the drag because, again, I don't have an object moving through the fluid. I got just the fluid moving through the pipe. I'm trying to deliver the fluid, and when I try to move the fluid through the pipe, there's going to be a drop in pressure because of viscosity. And if then we get to such, say, a high speed that turbulence occurs, then the pressure drop is many, many times greater than this. We won't even have a formula to work with. In fact, there is no really way to solve this. I mean, even the greatest minds of the world have worked on this, trying to solve, is there a kind of a generalized equation we can give once you hit turbulence? And sadly, it just doesn't seem to have a mathematical solution. And so if you major in mathematics, I mean, this is something that I think every mathematician at some point in their life goes, oh, I'm going to try to solve this. This would be one of those amazing solutions if somebody can solve it. And it just hasn't been solved yet. So it's why we won't try to say what it is. I just want to say it would be really big. And that will be good enough for us. So turbulence would be a really, really bad thing if your goal is trying to deliver blood or deliver water through a tube. That's really kind of the main thing. All right, well, one more thing, and then we'll wrap up this chapter and take our break here. But the last thing that your author does is talk about diffusion, dialysis, osmosis, active transport. Now, he doesn't get too much into active transport for good reasons. Active transport is actually not really a topic for a physics class. Maybe I should say more about that. But in your biology class, you talk about the living cells adding energy and having some mechanism of moving materials through the cell walls. And so that's just a biological question and not so much a physics of the fluid. This is not what the fluid is doing. This is what the machinery that make up your cells do. And so your author just wants to point that out. That's really the only reason he brings up the word active transport. Let me start here then with those words. What is diffusion? How is that slightly different than osmosis? And how is that slightly different from dialysis? And how is that different from active transport? Well, let me start with diffusion. And the best way to kind of do that is to look kind of as a drawing of a molecule. I thought I would use this as an opportunity to kind of show you these bouncing BBs again and say, okay, here I have maybe these gas molecules. And so the mental picture I hope you have is that right here are all of these atoms bouncing around, ricocheting around. And it's random in nature. Some are going left, some are going right, some are going up, some are going down, some are going forward, going back. And wherever they're going to hit something else and change directions. In fact, they hit another one about 100 trillion times every second. So they keep changing their direction. They don't go very far. They change their direction. And so what would happen if you were just to put a molecule right here in the air? maybe it's a bottle of perfume. I'll open up a bottle of perfume, and that molecule, when it gets in your nose, you'll recognize it. You'll go, oh, that's a sweet smell. Or maybe it's a terrible smell, like maybe you burnt your food cooking, and now where does it go? Just the random collisions and how it spreads out is the process of diffusion. This picture here, I think, shows it well. You might say that it starts here and it moves along and maybe it hits another molecule. So it ricochets and heads off this way, hits another molecule. Heads off this way, hits another molecule. Heads this way, hits another molecule. Heads this way, heads this way, heads this way. And so we're trying to draw just kind of a random distance with a random direction. And you can see that even if the molecule is moving very fast, and I'll go back to this bottle of perfume. If I were to open this bottle of perfume, that scent, that molecule, believe it or not, is moving 300 meters per second. Does that mean that that molecule in 1 second will be 300 meters down the road, which means somebody 300 meters from me can smell it in 1 second? No. It means it will travel 300 meters in kind of a random collisional path. And since it's just as likely that it goes left as it goes right, as it goes up, as it goes down, it's probably not going to get very far, even though it's moving very fast. It will start to migrate, though. And that's what diffusion is. See, they're trying to say that if you draw all this, there is a small distance from where it finished to where it starts. Let's just say this is 1 second. This whole path may be 300 meters, yet the distance away, it's unlikely it'll go right back to the same spot. But of course, it's also just as unlikely it'll go 300 meters and not because it didn't hit anything. And so what are the statistical odds that it gets back to itself? Not much. What are the statistical odds that it hits nothing and it's 300 meters? Not likely. But if you play this statistical game, and I told you there's a lot of advanced mathematics buried behind this, it will be some minor small distance away. It will not be back where it started, and it will not be 300 away. It'll be a short distance away. And then your author says there's a nice equation for that. There it is. He says, how far away will it be? He says x. X equals, and again, one of these, like I said, kind of an advanced topic without proof. It's 2 times this diffusion constant multiplied by time. And so what I want to get for you is just how would I do this calculation? And so there is a nice little table that measures this diffusion constant. I think it was here. And they've given a couple of them. Some important ones here would be oxygen spreading out, or sugar, glucose spreading out. And so there is the diffusion numbers. Another thing to point out is how well does the oxygen spread out in water versus air. And you can see oxygen spreading out in water is a bit challenging, how small that number is, at least compared to air. Most of us don't think about the oxygen being available in this room. I'm sure you have many concerns in life, but coming to class today and wondering if there's going to be enough oxygen in this room was not one of them. You're like, okay, it diffuses around, and if I sit on this side of the room or this side of the room, the oxygen is going to be available to me and I will be able to breathe. But if you're a fish, that may not be necessarily the case. As the waves break and trap the oxygen, they start at the surface and it diffuses down. and there may not be much oxygen down there. And so you may get things like, dead fish particles that sink all the way down to the bottom. And they stay there because there's no life to decay it. Which actually then is what ultimately happens, is then it gets buried with soot, or silt, which becomes then rock, which then turns into oil, and so we have the whole petroleum cycle, this old plant life that didn't decay because there wasn't any oxygen, because it didn't diffuse down to the bottom of the ocean, because we don't have any oxygen. And it doesn't have to be very deep. The mouth of the Mississippi is an excellent example of that. There's so much life coming at the mouth of the Mississippi that they consume all the oxygen, and so you don't have to go very deep before there's no more oxygen. And then so all these dying fish particles are just sinking down to the bottom, and so it's just loaded with organic material down there at the bottom, because and I better keep going. That's what Ron's warning me here about. But I do want to look then at a quick calculation that your author does, because your author, I think I passed it, says, now that we know, here we go, this calculation right here, they're not a hard calculation, but your author then just says this. It says, using this equation, how long would it take, what is it? It says, calculate the average time for a glucose molecule to move 1 centimeter. So if I had a bucket of water, or maybe more interesting, if I had coffee and I poured some sugar and it sinks to the bottom, how long would it take for the glucose molecule to separate out and come up 1 centimeter, let alone 7 centimeters, which would be the depth of my coffee? And so your author goes through this, and he calculates the time, 1 centimeter, here's the diffusion constant for glucose in water, and it takes 21 hours. So nobody puts sugar in their coffee by pouring it and then just waiting for it to diffuse. Everybody stirs it. You're just not going to get the sugar to mix around in a reasonable amount of time. It will happen, but it'll be a long, long time. And that's really what the best thing I can say about diffusion. So diffusion is kind of this random collision, bouncing off each other, where they go. There's a nice little equation we can use. We'll use it, but that's diffusion. Now, to wrap up this chapter then, without any more formulas, your author then says, well, what then is osmosis? And I would put osmosis and as really the same as dialysis, because they're really like diffusion, except there's a barrier. And that barrier then lets things go one way or the other, or maybe stops one kind of molecule but not the other. And so that's kind of the important difference. And so your author's trying to say here, let's say this is the cell membrane, and you've got all these molecules in here. Some of them are too big to fit through the small pores. So maybe water can go through, but sugar can't. And if water goes through, we call it osmosis. If there are other molecules, we call it dialysis. So to me, these are one and the same. I suppose you guys in life science, there's a big difference between the two, because you might be focusing on water versus the other molecules. But for me, from a physics point of view, studying the motion of the molecules, this is the same thing. It's just really a matter of how quickly they can move through these walls. And there's different ways of moving through the walls. One way is they're actually holes, but again, the membrane is made out of some kind of material, and so it can dissolve in here. And so this picture is trying to show you how these orange ones actually get in the material itself. I'm kind of thinking of like this slimy liquid stuff that if I put water against the slime, the water gets sucked in, and then it can come out the other side. And so there's different ways it can move through a barrier, but that's kind of the difference. And that's really the end of the chapter. I will say that your author goes on to say, as I said in a moment here, that if you have osmosis, then, and so this is the movement of the water molecules through a barrier, if we have then a different concentration, and so in this case, the blue ones are supposed to be the small water ones that can move, and the big dark ones are the sugar ones that can't move through the barrier. You will see as they hit this barrier, it's more likely that the water ones will go to this side because there is a larger number per square centimeter, if you will, of water molecules. In other words, on this side, as they hit the barrier, maybe half of them are water and half of them are sugar. But on the other side, maybe 3/4 of them are water and only 1/4 of them are sugar. And so as a result, then, you have what we'd say a higher concentration of water, so it's more likely that a water molecule goes through the pore this way than a water molecule goes this way. So it's really this kind of random diffusion process with a barrier, and then a statistical probability based upon concentration. And so the rule we like to say is it will go from high concentration to low concentration. It makes sense. It's just a statistical randomness. And again, if there's just more on this side hitting the barrier, chances of them going through are greater than over here where there's fewer of them hitting than going through. So what ends up happening is you get more going through this side. And that's what this picture is trying to show. So after a period of time, your water is going to go through here. So this water level is going to go down, and this water level is going to go up. Now, keep in mind that as it goes up, you're creating pressure. And so as the pressure on this side increases, that tends to push them this way better. So eventually you reach a balance. Eventually you reach a balance point where the rate at which they go one direction is equal to the rate they go the other direction. Now, of course, the reason they go from here over to here is increased because they have a force, a pressure pushing them this way. And so we refer to that as its osmosis pressure. When do you get a balance? When does the statistical randomness on this side put enough water molecules over here to start to force them back at a faster rate so they are now balanced? And so that's what we refer to as our osmosis pressure. And so now this would be balanced. This would not go any higher. There's just some maximum height it goes to. And that, as they say, a back pressure pushing backwards would be the rho GH. Well, like I said, got to call it quits here. I'll just say one thing right here. Active transport, then, your author throws in here by saying, look, what is active transport? Well, active transport is when you actually move a molecule from one place to another, but there's some kind of machinery in the body, in the cells. They're actually grabbing it, moving it from one place to another. That's more of a biological discussion. You probably know far more about it than I do. You probably have been working with active transport, but we could have some kind of mechanism that maybe this wall opens up, it grabs a sugar molecule, it pulls it to the other side. And if your body does that, if your cells do that, that's an active transport. There's something in there. Your body's actually using energy. Your body actually has a machinery to get that stuff to the side it needs it. Maybe in the cell or maybe out of the cell. So maybe if it's nutrients, it goes into the cell. If it's waste product, out of the cell. But it's an active transport. But I just wanted to say how that's different. It's not something you would discuss here in a physics class. It's not a dialysis or an osmosis or a diffusion. All right, well, like I said, we'll call it quits here and take our 15-minute break. All right, Ron.